let's do an overview. So overview, see, I can't even write, never. Overview of the course of these lectures. So let's get a big number line. What is that? Okay, whatever. Here is 2024. Here is 0. Here is something like 2000 BC. Okay, we could go all the way back to maybe 20,000 BC, but that's too many zeros. BC. We're going to start in earnest talking about the Babylonians, a little bit about Egyptian, Chinese, Indian mathematics around this time. So 20,000 is like shank bones with markings in them. So this is actually, there is something important to discuss here, which is the notion that math is about number and shape. So there are these two competing things, number and shape. Can you see that in the back? Yeah, it's okay. Maybe I can zoom in a little bit over here. We'll talk a lot about number and shape and sort of the effects they have on the study of mathematics. So we'll get to the Babylonians. We're going to discuss, in fact, if time permitting, I can't look there. Here. Okay. I can just add 5 minutes, just 5 minutes late. Good. And we stop at 20 after. So when that says 15, that's when I stop. Good. Okay. Time permitting, and I think we will get to things like Plimpton 322 and the Yale Babylonian collection 7289. These are sort of important documents in the history of mathematics. We'll go to the sources and try to understand what's going on there. This will tell us something about the state of mathematics in the Babylonian culture. Let's just mark 1,000 over here, around 500. This will not be in order. So at 500 BC, we get Pythagoras, and the Pythagoreans, kind of a cult-like situation. But it's the beginning of the development of the axiomatic system for mathematics. So we'll talk about this in more depth later, but math, like the difference between engineering is a whole bunch of math, and then you build a bridge, and then the proof that the bridge works is that it doesn't fall down, right? There's not a proof. There's just, you have computed to high accuracy, and you have a high degree of certainty that the bridge isn't going to fall down, and here it is, and people are walking over it, and it's standing. That's the proof. That's not how math works. Okay, in math, the Pythagoreans figured out that what you need is the truth and the evidence for the truth as a pair. So it's not enough to say, this is what's true. You have to give the reason why it's true. So this is sort of the beginning of the axiomatic system. We'll come back to this, axiomatic treatment of mathematics. That comes to full fruition about 200 years later. So around 350 BC, we'll just call it 300 BC, we get Euclid. And Euclid is really the kind of a midpoint. It's a culmination of the development of this kind of mathematics to an extremely sophisticated level. But then other people after him, like Archimedes, Apollonius, people are going to take it way, way farther than Euclid did in his time. So there's a whole big mess of beautiful mathematics. We're going to spend a good chunk of time in this region here. In fact, in some sense, you get Heron's formula. Those of you know that is around 100 AD, Common Era. Hypatia is over here at 300. She's like one of the last, maybe more like 400. 400 is one of the last of this Greek tradition in, well, let me show you a little bit of, I pulled up Google Maps. Where are we? I see. Let's go. We're going to talk about this object in just a second. Here's Google Maps. Okay, so when we're talking about the Babylonians, we're talking about sort of Iraq. So here the fertile region, Iraq, a bit of Iran. Then we move over here to Egypt and Alexandria. So Greek mathematics largely takes place in Alexandria in North Africa. Then the Romans take over this region, well, around 0. But then there's So around, I'm going to call this 800, mathematics moves over this period. Mathematics moves kind of back to the Babylonian region, but now it's under Arab rule. So there's a Persian mathematician named Al-Khwarizmi, who we'll spend a good bit of time discussing. So this is a Persian mathematician living in Baghdad. Anybody recognize this name at all, Al-Khwarizmi, other than the people who already know? Yes? What does it sound like? Yeah? If you anglicize that name, what does it become? Algorithm. The word algorithm is this guy's name. And the word algebra is this guy's textbook. Okay, so this is a very, very important person in the history of mathematics. And there's lots, nobody lives in isolation. There's lots of people around him that are making important contributions, just like there's lots of people around Euclid that are making important contributions. Yes?
I've heard in other languages saying algebra and not algebra, and I just thought like, oh, they've obviously botched that.
We're botching it. Yeah, it's algebra. Well, that's again an anglicization of the true text there. I'm trying to learn your names. Don't tell me. Elitsa. Yes. Okay. So right. So that's around 800. We're back in Baghdad. Then let's call this 1100. You get the Crusades. So Europe starts coming down to the Middle East. It's not a happy time in humanity, but mathematically, they're picking up all the mathematics that was transported to Baghdad, which moves through China, through India. So again, we're looking at, let's zoom out a bit. So mathematics in China and India is being traded through these routes. So the Europeans, the big name here is Fibonacci. If you've heard of Fibonacci, the reason you've heard of him is because he brought I wrote a 4 and an 8 and a 3 and a 5 and a 1, and those are all Hindu Arabic symbols that Fibonacci learned from the Persians and the Arabs through sort of following the trail of the Crusaders back into the Middle East, and brought that knowledge back to Europe. And that's sort of, again, we're on this exponential curve where nothing is happening, but it's setting the stage for something to happen. In particular, okay, we'll talk about number systems maybe not that much, but in particular, this is one of the first instances where people are using a different alphabet for numbers and letters. And that seems like, so what? What's the big deal? Anybody see what the big deal is? Say it again. You mean that the numbers look the same in all different parts of the world? Yeah, although old Hindu Arabic numbers don't look the same. If you go to Jordan, you would not be able to read their numbers. They still use the actual Arabic number system, which doesn't look all that much like. You'll see resemblances.
Now we have 10-base system, so then you can set zeros, and that's different than using either 22 or 24 depending on the alphabet.
That's right. So it's not that they use different, that's a very good point. So first of all, the fact that we have a 0, we're going to talk about place value and the importance of place value. And the decimal system, which just, if there were aliens, they wouldn't, with 8 fingers instead of 10, they'd have a different number system. The fact that we have a 0 as a way of allowing us to represent arbitrarily large and arbitrarily small numbers without introducing new symbols for them. So for example, the Egyptians, they still had a base 10 system. They'd use the first 10 letters of their alphabet to denote numbers, the first 1 through 9, and then they'd have another number for 10, and another letter would denote 10, another letter would denote 20, another letter would denote 30, another letter would denote 100, and so on. So there's like, and this also changes over time, how they actually do it. Something you want to say?
Well, this system's also, this system's used in at least I know for Hebrew.
Yes, exactly. It's not unique to, absolutely. Hebrew still today is using or was revived to use the same mechanism that was being used by all kinds of cultures. It's especially prevalent in Egyptian because lots of Egyptian manuscripts have survived. Again, what we know about history is what history has allowed us to know. Okay, so there's lots and lots of things that happen that aren't going to be on this because they died out and we never learned about them, or I don't know about it, right? So you're absolutely right. That's exactly how Hebrew works. Modern Hebrew went back to the roots of how things used to be. And it was the first 10 letters, the first 9 letters stood for the first 9 numerals. And then you get a 10 and a 20 and a 30 for the next bunch of letters and so on. So Fibonacci is the one who starts bringing this mathematics to Europe. So that's like the beginning of, it's the precursor to the Renaissance. We're not quite yet at the Renaissance. Okay, then we start getting to things like, let's call this 1500. We start getting people like Viet. We'll talk about Cardano, Tartaglia. Let me just put Cardano, Tartaglia here. These are kind of important. We'll spend a good deal of time on the story of the cubic equation, because it's really the story of algebra. The story of algebra is trying to solve polynomial equations, and there was a major breakthrough around this time. Yeah, we'll talk about that story in detail. Okay, so I really need to zoom in here. There's a lot of stuff that's going to start happening. You get to 1600, and well, you have at the earlier part of the 1600s, you have Fermat, Pierre de Fermat, you have Descartes. Then let me put 1700 over here. Later in the 1600s, you have Newton. Let's put it over here. Newton, Leibniz in calculus, the Bernoulli brothers, the Bernoulli family. The entire 1700s, I can just put one name. Leonhard Euler is just dominating. There's hundreds of people that are contributing all kinds of beautiful, fantastic things. When we get to 1800, it's no longer possible to write down the list of names we're going to see here. We start getting Gauss, we get Dirichlet, we get Riemann, we get towards the end of the 1800s, into the 1900s, we get Hilbert, we get Turing. This is going to be the tail end. The only rate limiting step here is how many lectures we have. Okay, so we will constantly, so throughout, this is kind of like a big overview, but even when we're talking about stuff happening here, we're going to jump to things that happened in the future and discuss the ramifications of the stories happening at all these places. But very roughly, this is the timeline of where we're going, some of the names that we'll meet along the way, and we're just going to keep zooming in on each of these stories and unpacking what's there. Any questions? Yes.
Going back to your earlier question.
Yuri.
So what exactly is the significance of having a system that's separate from alphabet format?
Ah, yes, we never answered the question. Very good. Thank you. Yeah. So already with one letter, you can have an infinite number of numbers, because you can have an A and then AA and AAA and AAAA. And in fact, that's what things looked like around 20,000 BC. There was no representation. There was just a mark, a tick mark for each number. And you can represent an arbitrarily large number that way. It's not a very efficient representation for a number. That's a very good guess. Yuri?
Is it because there's now a formal split between the humanities and math is no longer
That's a great I don't know that there is okay, we can argue about whether there's a formal split happens at any point, or the formal split was already way back here. That's not what I have in mind. That's a very good point and a good guess. Don't tell me. I'm learning your names. Cindy.
Must bust that myth right away. No split in math that early from humanities. It was part of the liberal arts for a very long time, up to even now. Like, there's a reason why math departments are still part of like schools of letters and arts.
That's right.
But to the number.
So sorry, just before you go on, I interpreted this question. I interpret your answer as a formal within the university or whatever the learning system is. Is there a split between the arts and mathematics? And you're absolutely right. Mathematics still today resides in the arts. When you get a math undergraduate here, it's a Bachelor of Arts, not engineering or science. Mathematics is absolutely an art form. Please continue.
This is just a conjecture based off some other research I've done on symbolism in math. This is sort of like significant because it opens up this room of possibility where people are starting to use symbols for math. You're going to invent things now. The equal sign does not exist until like the 18th century.
Correct.
I don't know if the plus sign existed yet, but we're not limited by the font anymore of your language. We don't need to use the Roman numerals. We can just make up new symbols and new ideas from that. And
Yes.
that's it.
That's all very good stuff, and I agree with all of that. I have one very particular thing in mind. So in terms of using symbols to denote things, already you could say Euclid is doing something revolutionary when he draws not just a point, but he labels that point A, alpha. Right? So labeling things, giving names to things is very powerful, but you have to know to interpret that alpha not as the number one, but as the name of that point. There's something really revolutionary that happens right around here, and we sort of said what it was. It was the beginning of the modern understanding of algebra. When you have algebra, like what's hard about algebra? Yeah, don't tell me. Amelia. Yes.
They're symbolic of something else, or is representative of or like a broader concept, just like symbol.
Very close. I mean, that's a great point. It's not the point I was trying to make. Tell me, Eleanor. When you write 2x squared plus 4x plus 3 equals y, you have separated the notion of 2 from the notion of x. It frees the letters to be unknown. They're not numbers. X isn't a number anymore. Whereas if you try to write this expression with, if A means 1, and you say AB squared plus CB, you're like, is B a variable or is B 2? Right? So having an extra set of symbols exclusively for numerical value is something that's a lot of things we'll see here are mathematically trivial, but historically, pedagogically, and in terms of our ability to communicate with ideas with one another, extremely significant. So this is one of those, to me, one of those instances, okay, where something is like, well, duh, whether you use this symbol to mean a number or you use this symbol to mean a number, but a number that's unknown, you would never write 3 and say, I don't know what 3 is. Let's solve for 3. You see? Mathematically, again, all over the place, we're going to see things that you would never teach next door because it's just absolutely trivial. It's about how human beings communicate those ideas to one another. But the fact that we figure out better, more efficient ways of communicating with one another opens up the realm of possibility of what we can discover scientifically. Does that make sense? Okay. All right. Other questions? What did you think of my answer? Okay.
I think one to add on to this is like something like a plus and equal sign.
Yes.
And this hampers the development of algebra. Like the first algebra textbook, the guy invents equal sign because it was such a pain to write out like by word equals this every single time.
Yeah, and we're going to study exactly that right around here. So depending on if it's like Viet, who introduces, so 1550s, where we get something that starts to vaguely resemble modern mathematics. By the time, the reason I have Euler here is if you read Euler, Euler is the first instance where you can just read Euler and you understand exactly what he's writing. He's writing it in the modern way. That's sort of the chicken before, not the chicken, putting the cart before the horse, the chicken and egg, we don't know which goes first. That's the reason mathematics is the modern notation for all of, not all, but very, very much of mathematics. The plus sign, I agree, and equal sign came before. But when you write, when you write, okay, when you write e to the x equals y equals f of x, that the reason we write it that way is because we all learned from Euler. Euler was just so prolific and exploded. He was there on the ground. So when you have the development of calculus here, it opens up this entire world. And by the way, the ideas that Newton and Leibniz were uncovering, I should point out somewhere around here, 1400, you have the Indian Madhava. So there's an entire school in India that's discovering similar ideas, but somehow there's not a Bernoulli and then an Euler after Madhava that takes those ideas and explodes them in the same way that Euler did. So again, we're going to get to this stuff like in 6 weeks. I'm just planting some seeds. But the reason we write so much of modern mathematics the way we do is because Euler taught us the most efficient way to communicate that. in functional notation and in all the things that poor high schoolers and middle schoolers, whatever, are beaten over their heads with. They don't realize what a privilege it is to study mathematics in such a efficient way, and such you can put so much information in very few symbols that your visual cortex can manipulate in a much better way than when we read these guys. We're going to read entire paragraphs. When you take twice a number which has been multiplied by itself and add to that number added to itself and again until you've done it 4 times, and like literally this is what it sounds like, and it's impossible just cognitively. You have to load so much more stuff into your brain to be able to process that, as opposed to 2x squared plus 4x plus 3. Takes a second to say. Everybody knows what I mean. Okay, so that is, again, mathematically trivial and very, very important in the development of more mathematics as a result of not using cognitive load for understanding the problem. Okay, any other questions? Awesome. Let's get to actual math. Okay, so let's jump straight here. So one thing I would like to impress upon you is that 2000 BC predates the ancient Greeks by as much as the ancient Greeks predate us. Okay, so if we think of like Euclid, just 2000 years ago, Euclid would think of the Babylonians as 2000 years before him. All right, so this is really, really, really long ago. You would think things are so primitive. Actually, before we get to that, let's talk just a little bit about number and shape. So the development of, okay, maybe not 20,000 years ago, maybe 200,000 years ago, we're basically monkeys, and or 2 million years ago, depending on where you want to call that. So where do human beings start to differentiate themselves from animals? That's already an interesting question in the history of math, in the history of the development of things. So let me tell you a little anecdote. So here's an anecdote. I can really, not only can I not write, I can't spell. Okay. So imagine the following scenario. You have a forest with a bunch of trees, okay? And you have these birds. I'm really testing the limits of what I can do. So you have these birds, they can go up high in the trees and then they're safe from hunters, or they can come down to the ground and feed and eat their worms, but then they're vulnerable to a hunter that wants to come. Okay, so scenario 1 is one hunter enters. One hunter enters the forest. So here's a hunter. Here's a, I don't know, we'll make it a shotgun, although obviously those don't exist yet. Enters the forest. The birds see the hunter. The birds rise. They fly up. They're on the ground searching for worms. They fly up into the trees where the hunter can't reach them. The hunter leaves. One hunter leaves. What do the birds do? They come back down. Yeah, back to birds come down. Birds come down. Okay, so they start eating it. Scenario 1, no big deal. They saw a hunter come in. They wanted to get away from the hunter. They know he's bad news. He leaves. They're like, okay, coast is clear. We come down. Great. Scenario 2, 2 hunters in. 2 hunters enter. The birds see hunters coming in. They rise. Birds rise. 1 hunter leaves. Any guesses? The birds stay up. Birds stay. It's not safe yet. They're high up in the trees, so they can't actually see the hunters, but they can see that in the clearing, 1 hunter is left. They saw 2 hunters come in. 1 hunter is left. Not enough. They wait. 1 more hunter leaves. The other hunter leaves. The birds go down. Go down. Okay. 3 hunters enter. Birds go up. Yeah, birds go up. 2 hunters leave. They see 2 hunters leave. They stay up. They stay up. 1 more hunter leaves. 1 hunter leaves. They go down. Okay, this is looking pretty boring. 4 hunters enter. Yeah, 4 hunters enter. Birds go up. 3 hunters leave. they come down. What can we learn about this series of events, this sequence of events?
It's hard for them to keep track of anything good through.
Yes. What do they know? They know 1, 2, and many. The bird's notion of a number is they know 1, they know 2, and then they know, I don't know, a lot. One guy came in, that guy left, no problem. 2 guys came in, 1 guy left, that's not enough, another guy leaves, no problem. Infinitely many hunters came in, only 2 came out. Stay up. 1 more left, I don't know how to do that arithmetic, I think it's safe, let's just go down, I'm hungry. Infinitely many came in, infinitely many came out, can't compute, coast is clear, go down. Do you guys know about, what's it called? Ordinals and cardinals? There's like, what are ordinals?
Ordinals like first, second, third, and cardinals 1, 2, 3.
Yes. So what are the cardinals? 1, 2, 3, 4, 5, right? These are the cardinals. And the ordinals? First, tell me, don't tell me, don't tell me. Laurie. First, second, third, fourth, fifth. Anybody notice anything? Not Lori. Tell me. Nargis. Yes, I'm asking a much dumber question. You're answering something very subtle. I'm asking a really, really dumb question. Do you notice something when you write out the ordinals and the cardinals in the English language? We've heard from Amelia. Tell me your name. Alexandra.
First, second, third is distinctly written entities, whereas fourth, fifth, they all end the same.
3, third, 4, fourth, 5, fifth. They're following a pattern. 1, first, 2, second. These words have nothing to do with one another. These words, first and second, appeared in the English language long, long, long before the notion of third, fourth, and fifth. We are birds. We are birds. Give me another language. Who speaks another language? Yeah, tell me how do you say one? How do you say these? Say 1 first, 2 second, 3 third, and so on in German. We got another language? Yeah. Arabic?
But 1 is Wahid, 2 is his name.
Give me 1 and then first.
Oh, well, I don't think we ever learned the oracles.
Okay.
But they do, in Arabic, they do, like second is a different category and first is a different category. If you're thinking about, plural versus singular, you have singular.
There's,
two, and then plural.
yeah.
And so that's something.
We got another one?
Apply, or sorry, one is yik, and then first is abadi. Dolvumi,
Interesting.
seven. Charlie.
Yeah. Is 1. Very interesting. Tell me Hebrew. So that doesn't sound so similar.
Nine, shnia.
Right. It already stabilizes. Yeah. Okay, so different languages, by the way, Russian doesn't stabilize until 5. There's a different, you say things differently up until 5, and then it begins to stabilize. So there's, just looking at language already suggests that there's much more to this story. We're going to spend 0 time on this, but I just want to point out that this is a really fascinating thing. The fact that we have number and we understand numbers greater than 1 and 2 and 3 and 4 and 5 is a miracle. Okay, and we didn't have that, and lots of animals don't have that. Don't tell me, Elitsa, and then Nargis.
If you have more information about this, that the birds don't know more than 4 versus it's the fact that they're doing some type of calculation in their head and they're saying, okay, so 25%, let's do it, but like 33%, like that's too risky.
Right. So that's a great question. And also the word birds is which species? Because crows know a lot more than maybe not. Pigeons always get a bad rap. I'm not gonna knock the pigeons. Yeah. So this is just an anecdote. It is something that I've read somewhere that people carried out this experiment. I don't remember what species of bird it was. Different species of birds have different limits, but all animals, we are the only animal, as far as I'm aware, who have an arbitrarily large understanding. And even that, we don't really have an arbitrarily large understanding, but we have, at least in theory, the capacity to understand arbitrarily large numbers. Like when people talk about millions and billions, we have no idea what the hell we're talking about. Nargis, you wanted to say something?
Very isolated human groups that have been proven to, because they're still mainly based on like hunting and gathering, they still don't have, like they understand the concept of a lot of things, but they still don't have like words for naming maybe 20 things versus 10 things.
Yeah, you don't need them. And for a long time, we didn't need them either. It's only when our societies became much more sophisticated in how we trade, in how we tax. There are 2 certainties in life. You guys know what they are? Death and taxes. Death and taxes. Everybody dies, and you're going to get taxed, right? Which is related to the millions and billions. Which animals don't tax one another. Well, okay, we can argue about that. So if you look, one of the earliest places where this kind of thing is being developed is the river Nile is constantly, and Cairo is like one of the big centers of development of mathematics. That's not an accident. This is where shape and number really come together, because you'll be taxed by the amount of land you have, but the amount of land you have changes from year to year because the river floods and destroys all things and everything moves around. And you're like, well, what's my land? What's your land? Like, how much do I owe the pharaoh this month? Right. So, so shape and number actually move together in a certain sense. Can I not scroll? I can. Please. Yeah, I have to say please. Shape and number. So by shape, I mean like, and we're going to get to shape very, very soon. In fact, the very first chapter is about shape and quadrature and understanding what that is. We're going to get to that. Maybe not today, but at least this week. Yes.
Why there was the difference between like 1 and first, 2, and 2nd, and 3, 4, or is it just the language barrier?
It's a historical. This is above my historical pay grade. You have more to say about that?
Well, I learned about cardinals and ordinals when I was learning Latin and ancient Greek, because it's just that one's a noun and one's an adjective.
Yeah.
It's like
No, but I think your question, so that's a great point, that the difference between cardinals and ordinals is one is a noun, one is a thing. First is yeah, it has to, yeah, it's the first person in line, the first what? Right. So these are the ordinals are adjectives. Yeah, let's put this. These are ordinals, and you should think adjective, whereas these are cardinals, and you should not birds. Sorry. You should think now. That was sorry. You should think now. So there's 1. How many were there? There were 2, as opposed to the second what? Second baseman, second whatever. I interpreted your question as slightly different. Sorry, tell me your name again. Allison. I interpreted your question as what have we learned from this? The only thing I wanted to point out is that language develops organically, historically over time, due to and English is one of the most bastardized languages there is. It's half German, half Latin, half French, half right. It's like all over the place. So even in a language as modern as English, I don't know if that's a correct adjective to add to it, but even here we can see the the development over time of the need for more precision. And once that precision was required, we just naturally followed a pattern to go from cardinals to ordinals, or maybe it was the other way around. I have no idea. But the point is that things stabilize after a time. These words were around long, long, long before these words were around. Does that make sense? Okay, so that's a little bit of the discussion of what was happening 20,000 BC. Let's skip 18,000 years and go to the Babylonians, 2000 BC. Okay, so we go to, what do I have queued up? Let's go to, yes, the Yale. This is, let me just copy this over here. Copy image and paste. Beautiful. Please. Love technology. If there was a way to give this these lectures on a blackboard, I would love to do so. But I want to show you pictures. I want to show you maps, and you don't want to see my attempts at maps or pictures of these things. So let me talk while this is loading. Okay, yeah. The thread of talking made it type up. Okay, this is called YBC. Please. This is called YBC, the Yale Babylonian collection. There's thousands and thousands of, you start digging in Iraq, in Iran, in Syria, and you just find stuff. And the stuff is all over the place. You can, I don't know how they dated this to something like 1800 BC. It's this big. So the last time I taught this course, I was at Yale, and we literally went next door and they showed it to us. And it's a little thing that fits in the palm of your hand. You have a little pen, and you can make a mark. You can make a big mark. That means 1. You can make a side mark with the other side, and that means 10. And so if you follow through what this is, along this line down the middle is a 1, then there's 2 10s and 4 1s. So that's 1 and 24. So I'm just going to write down the numbers that we see here. 1, 24, 51, and 10. Okay, you just start. This is all that was discovered. Let's forget that we know anything about anything. You're digging in Syria, you find this little rock. You see that, I mean, clearly there's something geometrical going on. Someone drew a square and drew a diagonal across that square. And then there's a bunch of markings. And your job is to uncover what the hell is going on here. So let's see if we can make sense to this. Any guesses? So not from people who already know what this subject. How many people already know what the subject is and what it means and what's going on here? Yes, awesome. Okay, everybody's going to learn something. What do we? Yeah, go ahead.
I think these sorts of things are often like,
Lori.
yes, the records for trade or storehouses and things like that.
Very, very good. That's exactly right. Many of these documents are actually carrying information that's not purely theoretical. Apparently, this was something like a 15-year-old's homework, which will tell you something about what was going on. Maybe a 20-year-old, I don't know. But it's apparently like a school exercise. So do we know anything about, speaking of number systems, we had a little discussion about number systems. Do we know anything about the kinds of number systems that the Babylonians were involved in? Does anyone have the time? How do we do time? How many minutes are there in an hour? How many seconds in a minute? Where does that come from? That's 5,000 years old, is to divide things into base 60, not base 10. Okay, so they have what's called a sexagesimal system. Sexagesimal system, so do we. Sexagesimal system just means base 60. So let's spend just a minute talking about what is this number 7289? What does that mean? The beauty of the numeric system, the Hindu-Arabic mechanism by which we can communicate with one another, is that this 7 doesn't mean 7, it means
7 times 1.
Exactly. It means 7,000, which is 7 times 1,000, which we can think of as 7 times 10 cubed. 1,000 is 10 cubed. And the 2 doesn't mean 2, it means 200, which is 2 times 10 squared. And the 8 doesn't mean 8, it means 80. And we're very used to this, which is 8 times 10 to the 1. And the 9 doesn't mean 9. Well, it does. It means 9 times 10 to the 0. Okay, so that's our decimal system. What's a sexagesimal system? Beautiful. Okay, now there are some things missing from the Babylonian sexagesimal system, namely this symbol, 0. So they have a problem with place value. They can't distinguish. If you wanted to write 7089, what you would do is that.
Is there any kind of conjecture about why they chose 60? You can ask the same, but why we chosen 10?
Yeah, why we chose 10, you know, yes, it's not a proof, but it's pretty clear why 10. There are all kinds of conjectures about why 60. 60 is a very nice round number. It has lots of divisors. There are about 360 days in a year. So if you think of, by the way, how many degrees are there? 360. Why? We don't know. No, not why are there there are about 360 days in a year. There are also 360 degrees historically going around, right? This is 360 degrees. If you take so we can argue that maybe that's related to the number of days in a year, and we see the cycles. You know, the Babylonians knew all kinds of amazing astronomical things. Maybe not amazing on the scale of what we know today, but you know, there was a big industry of trying to predict eclipses. Did anybody go to the eclipse in April? Did anybody go to totality? Yeah. What was that like? It was insane.
Yeah. It was like night.
Yeah. You're just standing there minding your business. Let's say you didn't know it was coming. You have your sheep, your whatever, everything's going fine. God turns the lights out. You look up and go, what the hell happened? Is that a cloud? No, it's not a cloud. There's a black eye staring at you. Quick, sacrifice a virgin or something. Let's, get the lights back on. And then 2 minutes later, the lights come back on. You're like, oh, thank God that the lights came back on. Now we can, remember whatever we did now, if that ever happens again. So the act of being able to predict when that happens, imagine how much power you have. You can say, I'm talking to God. So they're all the older things in math, in fact, until almost Kant, math is very often used to interact with more philosophical things, religion, astronomy, right? There's no differentiation between astronomical events, mathematics, science more broadly, but we will make that distinction. So imagine, okay, the Babylonians knew a whole lot of things astronomically. They, let's say, knew that there was about 360 degrees 360 days in a year, and they understand the cycles as things move around. If I were to put an equilateral triangle here, how many equilateral triangles will fit around? 6. 6 equilateral triangles will perfectly fit around this angle and make a hexagon, form a hexagon. Okay, so if we think of this angle, equilateral triangles, like you would think the most rigid structure, everything's the same. The angles, if we think of these angles as meaning 1, how many of those angles go around? 6. 6 of those angles go around. If we wanted to be more precise, how could we break up that 1? We can call that 1 60. And if we call that 1 60, if 60 is the same thing as 1, just like so in the decimal system, if I were to write 1 and nothing here, we would know that we mean 10. By the way, how do you distinguish 7,089 from 70,089? If you don't have a 0, you leave a slightly larger space and you hope to guess it right. Okay, there's all kinds of problems that the 0 solves. We also don't have a decimal point at this juncture. Yeah, so 1 really means 10 in the same way that if we think of that 1 as 60, that 1 really is a 1 and nothing after it, meaning 60, then around, all the way around, we get 360 degrees, which is very close to the number of days in a year. And you say, okay, maybe that's a good way of breaking things up. Okay, so I have no idea why they use 60. The reason we use 60 is because they use 60. The question is, why did they use 60? And I don't know. There's other things. There's, for example, you have, what are these called? Phalanges on your fingers. And you have 12 phalanges that you can easily access by counting. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12. 1, 2, 3, 12, by the way, 12. 12 hours on a clock. Again, another 12 is 2, another 12 is 3, 4, 5, 5 12s, 60. Okay, so people have all kinds of hypotheses about why that number in particular. It really works very well. Eventually, we went away from it because, by the way, even within base 60, they're writing in base 10. 24 is really 2 10s. So you can have at most, this number 51 is the largest number of 10s you can have. You can have 5 10s. This is 5 10s right there, and a single 1. And then this is a single 1. This is a single 10, rather. Okay, so they're writing in base 10 inside of a system that's base 60. That's kind of weird. Okay, so let's say you're a historian of the Babylonian tradition, and you already know that. So then you see these numbers, 1, 24, 51, 10, and you say, well, they also don't have a decimal point. So maybe 1 represents really, truly 1. What does that 24 represent? If I had a decimal point, if this was 0.3, what would that mean? That 3 means 10 to the minus 1 times 10 to the minus 1, right? Which is the same thing as divided 3 tenths. We even say this is n 3 tenths and 32 hundredths and so on. Okay, so we have this 1. Let's say there's an implicit decimal point there. What is that 24? What is it? Why do you say 2/5? You're doing something much more complicated than what I had in mind.
It's 60, so that's 1/5, but then it's times 2, so I made it 2/5.
I kind of see what you're, yeah, well, okay, no, I see exactly what you're doing. Awesome. But they wouldn't think of it as 2/5. Let's come back to, you're absolutely right. Now I understand what you're doing. They would just leave it as 24 over 60. 24 over 60 is 2/5. You're exactly right. But let's just think of it as naively as 24 over 60. Okay, let's not simplify. Okay, if I divide top and bottom by 12, I get 2/5. I love it. You're doing much more than I was trying to do. Okay, then what would that 51 mean? Over 60 squared. Because that's the next place, sexagesimal place after the sexagesimal point. It's all hard to say all these things. What would that 10 mean? 10 out of 60 cubed. Okay, and now we need a calculator. Let's pull up Wolfram Alpha. So, can you guys see that? We had a 1 plus 24 60ths plus 51 over 60 squared. And the nice thing about Wolfram Alpha is it knows what to do. I don't have to put parentheses. It knows PEMDAS, which is another human creation to allow us to communicate with each other more effectively, as long as people stop posting PEMDAS things on Twitter or in the New York Times, whatever the case may be. Okay, so this is the number, seemingly, that represents. And here's that number's decimal expansion. Okay, so I'm just going to write this down. 1.41421. This we're trying to unravel this puzzle. So one hypothesis is that's what this number represents. If that's what this number represents, then it's 1.4142129 212 414 is easy to remember. It's my old cell phone number. Okay. What if you do it what other way?
When I do a calculation, you're like, oh shoot, I thought I was just gonna get a big number, I got a small one. So then here you would just do 60 divided by 24. 600 divided by 50.
Oh, very interesting. Yeah. What if who says that they write their numbers the way we write our numbers, where this number means 7,000 as opposed to this number meaning 7,000? In what order should we write things? They do write left to right, unlike Hebrew and Arabic, which goes right to left. So they do write left to right. And so you have to know enough about the Babylonian tradition to start to infer these things. I thought you were going to say, how do you know the decimal place belongs there? Well, you could try it in all kinds of other places, which corresponds to multiplying this number by 60 or 60 squared or dividing it by 60. And you might not recognize what this number is if you moved it in the wrong place. Amelia. No, I'm sorry, Alexandra. Yes. I mean, sort of, yes.
Diagonal sides, so how do we know what the diagonal represents and where it fits into this?
We're just trying to figure it out, but we're going to come back to what these other numbers are, this 30 and the 42, 25, 35. We're going to come back to that. We're going to unravel this mystery.
Oh, I looked at the decimal based off of this line, it would have been at 20, between 24 and 50.
Oh, why? Just, yeah, the grid is that they drew the two diagonals of the square before they did the homework. It's like, it's anyone's guess what this really means. And let's try to figure out what the interpretation is. There's all kinds of different ways to interpret it. I'm going to show you one way, which turns out is a way that makes everything make perfect sense. If you believe that that's what they were doing, who knows what they were doing? These could just have been random dots. For all I know, I'm a mathematician. This is how you get out of jury duty if you're a mathematician, right? I was in New York City. I got voir dired, which means you have to go into the jury box. And they're like, you know, the proof, there's a criminal trial, there's a difference between criminal and civil. Civil, it's the evidence must be compelling beyond reasonable doubt is criminal. Yeah, it's much softer for civil lawsuits, but for criminal, it's beyond what a reasonable person would be able to doubt. I'm a mathematician. The only evidence that I accept is beyond any doubt whatsoever for the rest of humanity. Okay, you're off. You're off the jury. So, so you're absolutely right. I have no idea what's really going on here. I can conjecture the same things that the people who analyze this conjectured and tell you what their conclusions are and tell you why their conclusions make sense to me, but that's the best I can do. Tell me your name again, I'm sorry. Allison. Because it was a guess. And it's the guess that turns out to explain everything, that at least insofar as it's an explanation I'm willing to accept when I'm in the jury box, not as a mathematician, but in the jury box. Don't tell me, Amelia.
Where did we get that, or is that just a given?
We had to figure that out, and the people that discovered this object, wherever it was, I forget if it was Syria or Iraq or it was somewhere in ancient Babylon. So do you have an answer to that?
Finish whatever you're saying first.
I was going to say, let's take that as a given that we understand enough about how Babylonians communicated number to one another, that they would use this system with the two-sided pen. It's like a stylus, and this way means 1 and that way means 10, and they could just very efficiently put these markings in. Let's say that we knew that they used base 60 and that we knew that this is how they use base 60.
Not about y'all, but our decimal looks similar to the decimal value of 2.
Yes. Okay. Very good. Very, very good. Someone, don't tell me, Cindy. Yes. Cindy is noticing that this looks an awful lot like, what is root 2? Tell me what the square root of 2 is. Not sort 2. The square root of 2 is 1.414213. So notice that the square root of 2 is 1.414213. We're off in the 10, 100,000, 10,000, 100,000 millionth place. So this number agrees with this number. So these two agree to a precision of 1 over 10 to the 6 on that order. This is why I consider this mathematics and not engineering. Okay, so first of all, there's a whole bunch of things that we can learn from this calculation. Okay, so maybe not all of you know root 2 off the top of your heads, and maybe this, but why should you have thought of root 2? Let me draw the square. Yeah, Amelia? Yes, and what kind of right triangle? It's not just any right triangle, please. Thank you. It's an isosceles right triangle, right? If you take a square, I'll draw the square the usual way we see it, and you cut it in half, you get an isosceles right triangle. And so if you say that this side length is 1, and this side length is 1, is there a theorem that we know about right triangles? The Pythagorean theorem. By the way, this is 1500 years before Pythagoras. So the Pythagorean theorem is definitely not due originally to Pythagoras. It's known all over the place, the Pythagorean theorem. And the answer is exactly right. So if we call this unknown value C, thinking of A as 1 and B as also 1, the Pythagorean theorem says that A squared plus B squared equals C squared. A and B are both 1, so this is 1 squared plus 1 squared, which is 2. C squared is 2, so C must be the square root of 2. And this homework assignment was work out the square root of 2. Let me give you a chance to write. Some of you are still writing. Here's what we think this homework assignment was. Work out the square root of 2 when the side length of the square is 1/2. How would you write 1/2? Undo what you did when you turned it into 2/5. What's 1/2 in base 60? 30/60ths. That's what this 30 is. It's 0.30. So this is 1/2. And if you work out what this number is, it's root 2 over 2. It's half of this number. So this 15-year-old remembered what the square root of 2 was that he was taught in school, and then was supposed to do it for a square, not a 1 by 1 square, but a 1/2 by 1/2 square, and took this and just recorded this number and then divided it by 2 and got that number. And that's what we think is going on here. So that's what I mean by when you put all of those different pieces of evidence together and they all give you something to very high accuracy, you go, that's probably what was going on. Beyond a reasonable doubt. Or beyond some amount of doubt. That's what I also think, and I've been told that that's what people who are actually experts in this stuff think is going on in this picture. But what I can, with precision, compute is the fact that this number is within 1/1,000,000th of actual value of root 2. Layla. Yes, let me try to write it down. So, in fact, this is an opportunity for me to type instead of subjecting you to my chicken scratch. So my conjecture, or I don't know if it's certainly not my conjecture, it's other people have conjectured this too. Conjecture, this was a kid's homework assignment. Oh, you autocomplete, thank you, autocomplete. This was a kid's homework assignment. The main diagonal was perhaps a reminder of the root 2 learned in class, and the student was asked to work out the diagonal for a 1/2 by 1/2 square instead of 1 by 1 square. Maybe. Okay. So that's possibly what was going on here. Should we do another? Oh, do we have time to do another? No, we have 2 minutes. Okay. Let me show you what the other one is. We don't have to spend any time on it. I'll show you what, there's a whole bunch, this is number 7,000. So there's tens of thousands of these little pieces that people have found. The vast majority have not been analyzed. If you would like to do a PhD in a serology or something and go and analyze the next 100, and can you imagine how much time it would take to sit there and unravel all of this? It didn't happen in a half hour. the way we did it, because we knew where to look. Okay, so let me show you another one of these, and then we'll go. Another fascinating one is called Plimpton 322. It's the Plimpton collection. This is housed at Columbia University. So again, if you want to take a trip up to New York City, you can look at these things and you can touch other ones like it, not the original, and you can hold replicas, and you can, the people are very friendly. You can ask them about it. So here's Plimpton. That's a massive database. Again, presumably some students' homework, which has this first thing, if I remember, I'm not going to remember. It's like 119 and 169. I'm going to say that this big thing, its first entry is 119 and 169. I think that's right. I think this, if you work out what this is 119, and that is 169, if memory serves. In fact, here's a 2, which gets us 120, and then this is 69. Sorry, 59. 49? 49. Yeah, that's a 2, that's a 49. I claim that this is 169. And here's the thing, if you take 100, so I claim that these are Pythagorean triples. So if you take 169 squared, I think there's a triangle, there's a right triangle with one side 119 and 169. So if I take 169 squared, where is my calculator? Here it is. 169 squared is 28561. 28561. If you take 119 squared, 119 squared is 14161. 14161. So if this is the hypotenuse, this is c squared, and this is b squared. If I subtract the two, I'm going to subtract these two. I think I can actually do this. 61s cancel. The 5 is a 4. The 8 is a 4, and that's a 1. 14400. Can't believe this worked out. Is anybody recognize this number? Well, it's 144. 12 squared, and there's 100. So 120 squared. 120 squared. So this is 120. So these are massive tables. These are not numbers you would find by guess and check. These are massive. This thing that we're staring at is a list of 15 massive Pythagorean triples from 4,000 years ago. Okay, when you unravel what every one of these entries is. And you can imagine, how did they come up with such large numbers and check that there's, work out, like this took us 10 seconds to work out. Well, first of all, we used a calculator, but even if we didn't use a calculator, it'd take us 30 seconds to work out by hand because we have the Hindu Arabic numerals. All right.